Polysilicon consists of many small grains of silicon, which will be doped with phosphorus, an N-type dopant, to make them more conductive. With photolithography and the next mask, the polysilicon layer will be etched to create the gate electrodes that turn transistors on or off. To carefully control this etch step, the polysilicon is dry etched. The width of these gates determine the distance that separates the source from the drain of the transistor, and ultimately the speed of the circuit. The remaining photoresist is removed once again. The gates become the first conductive layer connecting to different transistors. Mask number 4 allows the implantation of the N-channel regions with a high concentration of N-type dopants to form the highly conductive source and drain regions of the N-channel transistors. Mask number 5 uncovers regions in the P-channel transistor, which are implanted with a high concentration of boron, a P-type dopant, to create the source and drain regions of the transistor. The photoresist is stripped, and again, the wafers are cleaned. In a furnace, the wafers are annealed, and defects created by ion implantation are repaired. Next, a thick insulating glass layer is deposited. The many different layers previously deposited and patterned are completely covered, leaving an unleveled glass surface with varying depths of fields. To ensure every part of subsequent mask patterns are transferred in sharp focus, the surface must be planarized. A chemical-mechanical method is used to polish down the thick oxide layer on the wafer surface. This creates the flat, level surface required for producing high-resolution patterns. Photolithography and mask number 6 define the openings through which the metal wiring will be able to contact the source, gate, and drain regions of each transistor. By plasma etching the unmasked portions of the silicon dioxide, contact holes are created. Through the microscope, these holes are seen as the small dots. In most chips, these contact holes are so small they must first be filled with a metal plug to ensure a solid electrical connection. Tungsten metal is deposited over the surface to completely fill these tiny holes. In a metal etcher, the top tungsten layer is then etched or polished down to the oxide layer. This leaves tungsten plugs in the contact holes, connecting to the polysilicon gate and the source and drain. A layer of an aluminum silicon alloy is deposited onto the wafer to become the first level of circuit wiring. Mask number 7 patterns the aluminum. This is the first level in which individual transistors are wired together to form complex blocks of circuitry. The excess aluminum is removed using dry etching, and the photoresist is removed. This leaves narrow metal strips which extend from one transistor to another and form the first layer of wires connecting the circuitry. In sophisticated circuits, the wiring is so complex that it is impossible to complete with a single level of aluminum wiring. Several additional layers of wiring are often produced on the same circuit. This SEM photograph shows a device with 2 metal layers. This cross-section shows 5 metal layers. Each additional layer typically requires at least 2 additional masks and the following process steps. Deposition of silicon dioxide to electrically insulate one layer of wiring from the subsequent levels. Photolithography, masking, and etching to open contact holes between the top layer of metal and the next layer to be deposited. Deposition into the contact holes of another tungsten plug. This ensures a good electrical connection between wiring levels and a more planar surface. Deposition and patterning of the new upper level of aluminum alloy. After all of the desired levels of metal interconnects are in place, a final layer of silicon nitride is deposited to protect the fragile aluminum interconnects. In the last photolithography step, only the nitride on top of the bonding pads is etched away. The white aluminum pads are all along the outer edges of this chip. They are the contact points between the wires from the outside world and the integrated circuit. The wafers are then stripped to photoresist, and the run is complete.